Okay, so I am jumping back into the Ethereum codebase. I have dug a little bit into the peer-to-peer folder now, and there's only really a couple little things I want to dig into now, and it kind of relates to this like Discover 4 and Discover 5 stuff. So not fully sure what their purpose is. It's kind of like there's a little bit going on. It's a V5 wire I think I probably want to start with, maybe. I might start with, let's start with this folder. Node looks like a very healthy file name. And it's not very big actually. Really is all in that table. Maybe I'll start with Node and see what it does. Is this just going to be... It's just going to be keeping track of what a node on the network is, I guess. So this goes into ENode. The node struct is an ENode. And just some little stuff around it. And then it's got a public key function. It takes a key and then encodes it. That's not super interesting. Decoding it. Not sure why they need to encode and decode a public key. Key.x, key.y. And then it's just got an ID which it dives into the ENode ID. Oh, encoded public key is the structure. Function inc public key. It's just 64 bytes. So this doesn't look very interesting at all. Wraps an ENode and returns this node. They even call it wrap. So it's just, they don't do anything with it. They're just making it within the namespace. Okay, uninteresting. Already didn't want to look into that. All right, let's go into V5. Let's see what it's doing. ls.alh, and we've got our biggest one is this message. It's got a message and a session. All right, what's a message? It's still a pretty small file. Wait, really? Is that right? Message was 7.6 kilobytes. Encoding, no it's not encoding. So this has 600 lines. Concurrent who are you tiebreaker. So we've got a header which is a packet header. A static header. Who are you auth data. Protocol ID is just 6 bytes. Got some errors. This is all very boilerplatey. So they're sharing Discovery V5 packets. So it looks like, and I kind of half knew this already. I don't really want to Google it because I want to kind of see if I can feel it through the code what this like Discovery V5 is. And within 2 seconds of looking at this, it kind of goes, it's how the packets are sent over the wire. So it's kind of like even lower level than whatever else is going on. So it's kind of like you open up a HTTP connection maybe. maybe not even that, maybe it's just a TCP connection and they're sending these sort of packets over top of it. So we've got our header and it describes how to make that header. Encodes a packet with random content. Who are you packet goes to an ENode ID. Encode handshaker header. Encode message header. Encode and decode. So we get a discovery packet, and this is probably where I want to try find. So we've got decode. So let's see if in this folder, in discover, in V5 wire, encode, decode. Decode message returns decode bytes. Is that all there is in it? This is a test one of it, yeah, crypto. Decode pub key, crypto test. So where does this decode get called from then? Not from here. So if we step up and go decode here, what do we find? Decode reads a discovery, so this V4 doing this something similar. That's where we were. There's a test. There's more in the same folder. Same folder. V4 wire has a decode. I suspect that looks at V4 though. So it's going to be in this V5 UDP. Cool. So V5 UDP exit / decode. It has an interface to V5. So here we've got handle packet, which is kind of what it sounds like. We've got a raw packet come in, we decode it, and it does something with it. And that's our codec, which is what was being defined in here. So where does this get called from though? If I go into P2P, P2P, and just see if I can find handle packet. That seems like it's got enough data in it to like describe where it would go. But even that, it looks like the only place it's defined is in the same file. There's no V5 tests. So at line 519, is another function, and this looks like it's receiving stuff in a channel. Dispatch. Dispatch runs in its own Go routine, handling incoming packets and dealing with calls. Any destination node, there is at most one active call stored in the T active call maps. A call is made when it is sent. The active call can be answered by a matching response, in which case the channel receives the response, or by timing A, in which case it receives an error. When the function that created the call signals the active call is done through call done, created the call signals the active call is done with call done, the next call from the call queue is started. calls may also be handled by a who are you packet. There's a who are you packet coming up again. So what does dispatch mean? This is just going to be underneath a service start, I bet. Dispatch read. Handle call response. Dispatches a response packet. Listen V5. So where is listen V5 defined? Peer-to-peer server is where it all lives. Okay, cool. So that kind of ties it back to where we were. Boot node also lives here though. So that's not going to be relevant. That's like something else. A boot node is specific node. So we're looking at a normal node. Dev peer-to-peer is, I'm not sure, but it's like its own executable. So I'm guessing it's like some test where they set up a dev peer-to-peer. But this server is going to be where it all is. So let's look into peer-to-peer server. And if I go to 606 and 608 is where it all lives. So if server discovery V5, then we set up config and we call this listen on V5. Where's this all being called from? It's going to be start the peer-to-peer server. Set up discovery. And here feels vaguely similar to what we were looking at in the last couple videos. Yeah, so start. So the service starts, at some point it calls set up discovery. Set up discovery controls whether or not we get V4 or V5. And we had our stuff for when we were sending and broadcasting on these like UDP connections. No, not these ones. These are Discovery V4, Discovery V5. If scon does not equal nil, calling the exact same thing with scon or con. Shared UDP connection. Cool. So we go into here and we're calling listen on version 5. Is that right? Let's just say it is version 5. I'm not actually even sure if we use version 4 or version 5. I assume it's version 5. So we call new UDP V5 and it gives us T. V5, which is right below. Didn't even need searching. Creates a transport, but don't start any of the go routines. Great. UDP V5 is just going to be a wrapper around it all. And it's called T. And we return that. So where's UDP V5 defined? P2P. Discover. And it's got to be in this file, doesn't it? what was it called? Udp V5. Not there. Everywhere. So let's see if we can refine that. Struct. And in here, it's not there. Okay. So somewhere in here is a definition of it somewhere. It is in V5 UDP. Type struct. Damn. So in here there's a type struct called that. MB. So it's here. Codec version 5 is implemented by V5 wire codec. Encodes a packet, decodes a packet. V5 wire codec. Cool. This is our structure we were looking at. It's just got a bunch of channels and it's got a connection. And that UDP connection is an interface. So it is defined. Yeah, in this common discover is a network connection in which discovery can operate. Yeah, cool. So it always got a connection. They can send messages over. V4 and V5 can send different things, I guess. Channels into dispatch, shut down stuff. So listen V5 gets our connection, calls t.tab.loop, calls t.readLoop, and calls t.dispatch. So first of all, what was tab in there? It's just a table. Okay. So here we go. We're starting to dig into table. Loop. Schedules runs of do refresh, we revalidate, and copy live nodes. Do refresh. Then we go into a loop and we check it. Do refresh performs a lookup for a random target to keep the buckets full. Seed nodes are inserted if the table is empty. Interesting. So this is those buckets that they were talking about, where it's like your distance from like your hash distance is put into a bucket, and then if you want to send something to someone, you send it to the bucket. Everyone in the bucket that's got a closest hash to it. Potentially what it's talking about. Cool. So we've got a table. It does a loop. It's keeping track of its own nodes in that table. Interesting. So how does this link up with the like database and all the structures, I guess? So anyway, back to here. We call read loop. Reads packets from the network. Read the next channel. We call read from UDP. If it's an error, we do nothing else if nothing. Otherwise we send to dispatch read packet. There it is right below us. And what we do is we immediately put it into another channel called packet in channel, which goes into the dispatch loop. So it comes in, and then we put it into a packet we've got to read. Where's this content and this from defined? There's content. So in here, we've got a buffer. And it reads from the UDP connection into the buffer, I guess. And then it passes that buffer into this read from packet. And then it puts it into this channel. So the dispatch channel kind of like handles it all in the end. So t.dispatch is where all the meat is. For any destination node, there is at most one active call. Okay, so we've got a message. It's read from UDP. We've got a bunch of bytes that we've got to deal with. And it was in packet in channel, I think it was called. So then we call handle packet. And we've got the packet data and packet address. And these kind of like timeouts and stuff seem less interesting, so I'll probably not call channel, but a call queue. Alright, so packet in channel calls handle packet. And it pulls out this address and it's got raw packets, and then it calls decode, which is what we're looking at before. And it gives us this packet back. What's that packet? P is called a packet, cool. Packet sizes, packet. I suspect it's not defined in here. CD P2P packet. It's an interface defined in V5 wire. What was it called? It was in V4 wire. And V5 wire, I guess. Message. Here we go. So a packet is all messages. So all messages have a name, a kind, a request ID, and a set request ID. So we've got message types, and there's quite a few there. And we've got our normal ping pongs. Find in node, find in. Cool. So this kind of feels like they've got their own protocol for nodes who want to find other nodes. And I guess it's such an important part of like the network that they want it efficient. And it's different from when you want to broadcast a block, because you don't really want to maintain. Nah, that list I still would feel should be the same. Like you'd have a big list of your peers, but you get a message, and that message is from other people who are looking to find nodes, and it goes to its own special area because they maintain its own list that just makes it efficient to reply with nodes. So maybe that's how it goes. So protocol messages unknown. Who are you contains the handshake. Challenge data. We encode a challenge. Ping pong. Find node is a query for nodes in a given bucket. Ah, so you have your bucket, and you want to find a node. So you call every person in that bucket, and you ask them if they've got that node's details. So if you're trying to find someone, maybe this is, so they've got a special sort of like messaging system for when you want to find a person. And I guess it probably, which would make sense, it's called discover, right? So you discover in another node. Decode message. Switch P type. So it finds P type, it's got a body, and it searches cases through them and creates a new one. And they're all implemented this packet function. So all these different things. So you can decrypted gets returned. Decode bytes into decrypted. Cool. So decode, who are you? That's not what I was looking for. We've got decode. So you call decode on this packet, this random packet that's come in. You are unsure what type it is. So you extract the header out of where? What's input? Length of input. Here. So it's just bytes. So you find the length of the input, which is its bytes. And then you get up to the size of masking 4, header 4, or IV, something vector. So you copy those bytes into this head's IV, and then you go into it and you find from that to packet data, and you get a static header out of it, and say that's a static header. So you got header and you got static header, and then you do a source key stream over it. What is that doing? A static header and static header. So this got some like special stuff going on. I don't want to say decrypting, but like kind of feels like it. And then binary read the static header into c.reader. What's c.reader? God, so many little things. Codec reader. You read out of the static header into this one. Okay, so you reset the codec reader, and then you put it in there. And then you know how big the data is. And on head, you check it's valid with that size. If it's not, you return nothing. Fine. You've got it in this codec now. They're going to call like decode. So auth data unmask authorization. This is really low level stuff. It's probably like not super interesting. But they pull out of this header what type of message it is. So it's a who are you or a handshake, a special types. Else it goes the codec decode message, and you pass in the other stuff. So really all it does is it splits the raw data that's come over the wire. It's coming here. Split it into static header and put that static header into this codec reader. And that codec reader, I assume, is going to be able to read what those headers say and interpret the binary and I guess dynamic data that comes in as part of the packet. So it's like, you know, the first X bytes are going to be the same because they're all got the same header. Then you chuck the rest of the data, which is message data. So it does some stuff with authorization here too. So decode message is probably where we want to go next. Head.auth data. How does head.flag get set though? What header? Mask, source stream, static header. Head static header to C reader. Yeah, I'm not actually sure where it gets that from. Probably uninteresting. Decode message. Okay, actually, so this is kind of like, all this is really doing is saying I've got raw data in this array of bytes. You check binary read. So decrypting it. And then try decrypting the message. So read key using the source ID, the from address. And then you use that key to decrypt the data that's in there. Alright, so these messages are encrypted, I guess, is all I'm getting out of this. Masking and unmasking. Alright, so I got a special way for you to check find someone on the network. You maintain a limited list of people in your like node list, but you do have to send messages to specific ENodes occasionally. Occasionally to specific ENode IDs. I don't think I actually want to dive too much more into that. I mean, it might be interesting to do if there was like a bug or something to work on, but I mean, let's look at table util test. Let's look at some tests and see what they actually do with it. So new table test creates a node which is log distance away. Nodes to records. Fill bucket inserts nodes into the given bucket until it's full. Fill table, so it's got a table of buckets. Ping recorder, ping recorder. This isn't even test. This is simulate an ENR request. So this is requesting for a specific node. And you dive into your records for end.id. Is that all? Not equal. These are table utilities test. But none of these are actually tests, so that's not what I want. What are we helping out with this table test? So we go into here now and we've got a bit more. Test table ping. So they make a test, call it in parallel, and test ping replace, which is this first one here. So we have a ping recorder, we make a new table test. So we've got a table. Fill up the senders buckets. Then we go into nothing. Do revalidate. We add a scene node. Do revalidate. Transport pinged. So it really just sends a ping message to this guy and says, and updates its records to say it did a ping, and then it's like, did it actually do that? So this is actually boring tests. By boring I mean like, hey look, we've made the structure and we called everything we needed to do to it update its records, and it possibly did that. I'm sort of losing interest in this folder, to be honest. What else we got? What's in DNS discover? .alh, equally low stuff. Client and tree. These are pretty small folders. Client discovers nodes by querying DNS servers. So, entire node tree at a given URL. Updating DNS discovery route. It's a route entry. Retrieves an entry from the cache or fetches it from the network if it isn't cached. Resolving entries. Do resolve entry. Random iterator. Traverses the trees and returns nodes found in them. And the other one was tree. So at some point we got a tree of nodes, I guess. Is a Merkle tree of node records. So returns all DNS TXT records. So it's like processing DNS, or is it generating it, or it provides a DNS? Here's a nice big comment. Let's see what it says. We want to keep the UDP size below 512 bytes. Efficient messages. So they're saying how many bytes goes into this DNS. Yeah, there's some stuff here potentially isn't super related to the P2P network, but they've built like a DNS sort of resolver. It's like a DNS server that can provide a, I don't know why it does this. Make tree. So we maintain a tree of DNS nodes. Root entry branch. Okay, this is just tree. That's a tree. And this is all stuff to do with it. So who has got the tree and why do we keep it? Let's get back up. New tree. New link. New legacy. Pass ENR. Why do we have trees? So you can call nodes. CD P2P, go into DNS discover. So it's a different way of discovering potentially who these are. Sync a tree. Client syncs a tree. Downloads the entire node tree at a given URL. So you can go to a URL and it will provide you with a tree of nodes. I wonder if this is like a default way of actually finding nodes, or if it's like a, we thought this would be a cool idea. In our tree. So sync. The client tree. No. Client. Sync tree. Is not called by this. This is outside of it. That's a bit more interesting. Sync tree. That sync tree is called not in here. So I don't think it's actually like a default thing. Like you don't by default go and sync a tree. Dev P2P DNS command. So is it specifically if you call this DNS command in dev P2P? Dev P2P DNS command. No, what have I done? Wasn't looking. DNS dis. No. Dev P2P DNS command. So in here, we've got sync tree. DNS sync performs a DNS sync, and it pulls the URL out of DNS sync. Is there a help on this? Downloads a DNS discovery tree. Signs a DNS discovery tree. This all seems super not relevant to like everyday Ethereum. I want to confirm that before I DNS tree Ethereum. We've got a special EIP node list. We turn our node list into a DNS tree. We publish that tree to a DNS provider like Cloudflare. And then once it is available, you can use it. Interesting. An Ethereum backend for the domain system. No. This is not recommended for general use. And it's relatively outdated. We contain hard-coded bootstrap node lists. Updating those requires a software update. Is a replacement for client bootstrap nodes with equivalent security and many benefits. Okay, so they're just trying to kill off the hard-coded stuff. I wonder how successful it actually was. So I feel like the hard-coded stuff is still there. But I guess, yeah, so they can put it into a DNS record, and that means you can just query a DNS rather than actually going and digging in your hard-coded stuff. So that's cool, but that is not super like important to managing a node. I wonder if there's anything else I really want to dig into here. I feel like I've done quite a lot. What do we got? Like, is there a block? Unblock. I'm really just scraping to see if there's anything else that seems interesting. I kind of think I went over it, so this might be the end. This is a block ciphers. Nah, I think this is that. I don't think there's anything else we want to really look into here. It's pretty low level. Probably be more interesting if you're like trying to find something wrong with it. So cool. I'm going to call it there. Thanks all for tuning in.